Alright, so today we're going to be talking about something called differentials. And essentially, differentials are basically like, so when we represent a derivative, right? Let's say we had the function y is equal to x squared. We write the derivative of x squared as dy over dx is equal to 2x. And this like dy over dx is not a ratio, even though it looks like a ratio that we're used to. It's not a fraction, right? It's like an operator. But differentials is the idea of like, what if in certain scenarios this this derivative does represent a ratio, and then in that case we can write dy is equal to 2x times dx. And the whole idea of writing this is we're saying that dy is how much our value of y changes when we are at a certain x, and then we pivot from x by this amount dx. So what we're saying is, let's say for this example I had like y equals x squared, and then I am centered at this value of x, right? And if I just pivot a bit from that x, and I'll call that my dx, this change in y dy is what this differential is estimating. And so to give a concrete example, if x is equal to 2, then I had like 2 times 2 would be, well, my slope. And then if I were to like deviate from x equals 2 by like 0.1, I'm saying that the estimate of how much y is going to change is equal to, so dy would be equal to 0.4. And basically my differential is saying, or it's estimating that if I were to deviate my x value by increasing it by 0.1 from the value of from x equals 2, then my y value would increase by 0.4. And this is not an actual representation of how much my y value increases. This is just an estimate. We can confirm this by just doing like if I were at x equals 2 and I were to increase my x by 0.1, then essentially I'd get 2.1 squared, right? Which is 4.41. And that is not an increase, that is an increase of 0.41, not 0.4. But differentials are basically just an estimate. We're creating a really crude estimate, a linear estimate of how much y increases as x increases. And this just helps us kind of relate rates together and how much stuff increases when I'm increasing my value of y. And where is like this idea of me being able to separate out dy and dx coming from? This all comes from what the analysis we did in linearization. Recall that when we were linearizing, we had a function L of x minus f of a is equal to f prime of a times x minus a. And this is the representation or the linearization of a function centered at the value x equals a, right? And so when we want to estimate how much a function changes, we're just saying that this becomes delta y, right? So because this was our original a, and we're deviating to a new value x, and the change in x would be x minus a, so that will be dx, and then f prime of a is essentially just the slope at point A. And so this linearization is just like a fancy way of writing out what we already saw when we had a linear approximate of a function. And it's just like a crude shorthand, I would say. It's nothing much than linearizing a function and using that linearized version to estimate how much values change as a function of x changing. And so let's use this idea of differentials to solve some problems. So let us estimate how much the area of a circle increases when radius increases from 10 to 10.1. So we know that in this case, area is equal to pi r squared. So if we were to use the notion of differentials, we'd get dA is equal to 2 pi r times dr, right? Because this is the derivative of our original function, and we're trying to estimate how much area changes as a function of our radius changing. Our original radius is 10, right? And we're increasing it to 10.1. So dr, which is the change in r, is simply equal to 0.1. And just plugging everything in, we have 2 pi times 10 times 0.1. And so we're saying dA is about 2 pi. And so really fast, through this like differential method, we got a estimate of how much our area is going to change. And this is not going to actually be the exact change in the area when we increase the radius from 10 to 10.1, but it serves as a close estimate, especially for small values of dr. And so that's like a really fast example. And so let's just do one last example of how we can use the idea of differentials to solve problems. So this question says, how accurate must our measurements of the radius of a sphere be to make sure we calculate its surface area within 1% of its true value. So basically what we're saying is we have some noise in the measurement of the radius of this in the measurement of the radius of the sphere, and how we want to like how permissible can this noise be to make sure that our surface area that we calculate with like the noisy measurement of the radius is within 1% of like the true radius of the sphere. So the surface area of a sphere is given by 4 pi r squared, right? And if we use differentials, we get ds, we can just ignore the a, is equal to 8 pi r times dr, right? So that represents like the change in surface area as a function of the change in the radius. Now we don't know the original radius like we did in the other function, but we know that we just want the value of the calculated surface area to be within 1% of the actual surface area, within 1% of the true value, right? So the true value of the surface area we already know is 4 pi r squared. And so 1% of that is just 4 pi r squared divided by 100, right? And the idea is we want to make sure, or sorry, this is the true surface area, and we want to make sure that the change is within 1% of it. And so the idea is this is the change, ds, 8 pi r times dr. So we want 8 pi r dr divided by 4 pi r squared to be less than or equal to 0.01, right? Because this is the change in surface area, and this is the actual surface area. And we want to make sure that that extra surface area that we see is within 1% of the true value of the surface area. And so some terms nicely cancel out over here. And then this. And so we get 2 dr over r is less than or equal to 0.01. And then we get 2 dr is less than or equal to 0.01 r. And then dr is less than or equal to 0.005 r. And that tells us that the noise, so dr kind of represents the noise, right? So the noise in the calculation of the radius of the sphere should be less than 0.005 times the actual value of the radius. So this means that the error in radius calculation and then ignore that. The error in radius calculation should be less than or equal to 0.5% of radius, right? And I just converted this decimal into percent, and that solves the problem. And that solves like what this problem's asking. So to make sure that our surface area, the like calculated surface area with the noise is within a percent of the actual surface area, we need to make sure that the calculation of the radius is, or the radius that we find out is within point, or like the error in the calculation of the radius is within 0.5% of the true value. And that's just the usage of differentials to solve various problems.